So hi everyone, and today we have the pleasure to host Dr. Yuhiko Aoyama for this week's Astro Seminar. So Yuhiko was educated at the University of Tokyo, where he obtained his PhD in 2019 with a dissertation on the theoretical models of gas accretion for constraining planet formation, and in particular on modeling of non-equilibrium microphysics. So he then moved for a postdoc at Tsinghua University, where he's now based. And his research interests focus on planetary and stellar formation and exoplanets. And today he will tell us about hydrogen line emission from accreting protoplanets. So please take it away, Yuhiko.
Yeah, thank you for introducing. Thank you for giving me a chance to talk here. I'm Yuhiko Aoyama. So let me talk about this title, hydrogen line emission from accreting protoplanets. In this work, my collaborators is Gabriel Marel in Tübingen University, Christoph Mordassini in Bell University, and Masahiro Ikoma in National Astronomical Observatory of Japan. So let's start with the background. Okay, so at first, let's start with why do we focus on the accreting planets? So accreting, planetary accretion means the accretion process or one of the formation process of the gas giant. So here, gas giant is mainly composed of the gas, such as Jupiter or Saturn. So this is a schematic image of the gas accretion of the giant planet. So giant planet is formed in the early stage of the planetary formation, and the planet is embedded in the gaseous disk and gather the surrounding disk gas. So gas in the protoplanetary disk surrounding stellar gas. So this process is really important, not only for the planet gas giant formation itself, but also for the other planet formation, because this accretion process changes the structure of the protoplanetary disk. So this gathers the gas and dust solid to the planet. So this process makes a large gap in the protoplanetary disk and change the distribution of the materials to form the other planets. And also this gap formation is related to the radial migration of the planet. So gas giant radially moves in the protoplanetary disk, and this affects the formation of other planets. Also, this gas accretion creates a circumplanetary gas disk. So in this gas disk, the satellite is considered to form. So this process is also important for the satellite formation. So this accretion process of gas giant is really crucial to understand the planetary system formation. So we focus on this accretion process. Then if we can, we want to directly observe or study the accretion process. Unfortunately, thanks to the recent improvement of the observational instrument, we can do it actually. So there is a survey on the forming planets. And in this survey, the target is a protoplanetary disk with large gap. So, as I said, the star have protoplanetary disk means a star or star system is young, and maybe the planet is in forming process. And this large gap infers the planet is embedded in the disk. And actually, this large gap can be made from other process like disk instability, disk wave instability, or something like that. But in most cases, people believe that the planet is embedded in this deep gap. So this left figure is one of the observational results. So this is a figure of PDS-70 system. So at the center of this figure, there is a star PDS-70A, and this blue color corresponds to the near-infrared photo detection. So it means here there is a photo source of the near-infrared photon, and this is a dust ring or dust disk around the PDS-70A star. And here in this black region, there is no emission. This means there is a gap and there is no material in this region. So this is a large gap in the protoplanetary disk. And in this large gap, there is a point source of the photon here and in near infrared. So people think that this is a planet embedded in the protoplanetary disk. And also, as shown in the red color, this planet is detected also in H-alpha photon. So this H alpha is really important to understand the accretion. So let's see this, SED or H alpha. So this is SED of the accreting planets. So the horizontal is the wavelength and vertical axis is flux in Miljansky. The red, green, and blue points correspond to the observational points. The red and green is in the near-infrared photo wavelengths, and H alpha is in the visible wavelengths. These black line and pink line correspond to the theoretically estimated disk and planetary photosphere emission, SED. So as you see, these red and green points are on the theoretically estimated line. So this means this near-infrared photo can be explained by this theoretical model. But as you see, H alpha is really far from the theoretical lines. This means H alpha is too bright related to the theoretically estimated SED. So let's see what is H alpha. So this line represents the principal quantum number of atomic hydrogen. So n equal 1 is the ground state of hydrogen atom, and n equal 2, 3, 4 is the excited state. So mostly in cool region, cool gas, the electron of atomic hydrogen is in the ground state. But when the fifth electron collides with the ground state hydrogen, then the electron is excited to higher level. Then the excited hydrogen spontaneously de-excites to the lower level. Due to the energy conservation, the energy between the electron level is emitted as a photon with specific wavelengths. So when the electron is de-excited from 2 to 1, then the photon is so-called Balmer-alpha. And when the photon is de-excited from 3 to 2, then the photon is so-called Balmer-alpha. But for hydrogen, the Balmer-alpha is specifically called as H alpha. So this is H alpha. So this means this emission requires excited hydrogen, and this requires a collision with free electron, and this requires hot temperature gas. So typically, the required temperature is 10 to 4 Kelvin or higher. And actually, in this pink line, people assume the 2,000 or 3,000 Kelvin of planetary photosphere. This is not cool, but it's not enough to emit H alpha. So this means this H alpha means 10 to 4 Kelvin, but this pink line or this red and green observational point means 10 to 3 Kelvin. This is controversial. So trick to explain this controversial is shock heating. So this is a schematic image of the magnetic accretion. So actually this is partially considered on the stellar context, but if the planet also have a strong magnetic field, this mechanism is considered to occur. So for planetary case, this is planet, and this is circumplanetary disk. And when the planet have a strong magnetic field, then the inner region of circumplanetary disk is truncated with a strong magnetic field. And the gas temperature is a few thousand Kelvin, so the gas is partially ionized. So the gas is well coupled with the magnetic field and flow along with the magnetic field to the planet. Then the gas velocity can reach approximately to the free fall velocity. And for planetary case, the free fall velocity is around a few or several tens kilometers per sec. Then just after the shock, the gas temperature can reach to 10 to 5 Kelvin or higher in some case. But as you see, as you see in the previous figure, the planetary photosphere temperature is much lower than this temperature. So the equilibrium temperature is 10 to 3 Kelvin or so. So this hot gas quickly cools to the lower temperature of photosphere. So this region is very spatially thin. So mostly we cannot see this region, including near infrared. We can see this deep photosphere of temperature of 10 to 3 Kelvin. But in hydrogen line, so actually hydrogen line have large opacity. So only in wavelengths of hydrogen line, we can see this hot region. So this is a trick to explain both of the hot and cool emission from the accreting planets. So we consider that the emission of hydrogen line coming from such a shock heating. So our purpose in this study is we want to construct the H-alpha emission model in shock heated gas. And by using this model, we want to reproduce the observation of H-alpha emission. And more, we want to get some information related to the accreting planet by using the model and observation of H-alpha. This is our purpose in this study. Okay, so let's move to the numerical details. But yeah, let's skip the two details and things. So let's see this red ones. So important point of this numerical model is the input parameter of our numerical model is gas velocity and density or number density before the shock. Then we calculate the shock heating and gas cooling and radiative transfer in the shock heated gas region. And finally, we get the hydrogen line flux emitted from the shock surface. But in the point of this numerical model is a time scale. So actually, in this case, the time scale of cooling gas and time scale of radiative transfer or electron transition have a similar time scale. So we cannot assume any equilibrium state for the electron level also. So we have to calculate the time evolution of cooling and electron transition and radiative transfer at the same time. This is the point of this numerical model. Then let's see the overview of the shock heated gas region. So this is one example of the gas property in the shock heated gas. In this case, the initial parameter V0 and V0 is this parameter. The velocity is 40 km per sec. So for example, when the planetary mass is 1 Jupiter mass and the radius of the planet is 2 Jupiter radius, then the gas free fall velocity is 42 km per sec or so. So this is similar to this case. And we assume the gas density for 10 to the 9 per cubic centimeter in this case. In this figure, the vertical axis represents the depth from the shock surface. So at the zero, depth equals 0, there is a shock, and we calculate the gas flow after the shock to deeper direction. So left panel shows the temperature after the shock. Just after the shock, the gas temperature can reach to 6 times 10 to the 4 Kelvin. And after the shock, the gas temperature quickly cools to the lower temperature, in this case, 10 to the 4 Kelvin. So it takes only a few hundred seconds and a few hundred kilometers to reach to 10 to the 4 Kelvin. So this is really quick cooling. Center panel shows the abundance of the chemical species or excited level of the hydrogen. Yes, do you have a question?
Yes, yeah, so I was trying to understand. So is the interacting gas basically the gas that is really, physically hitting the surface of the planet, or is there a significant amount of material that's actually accreting through bond-dipole accretion that's sort of being gravitationally focused, given the relatively low sound speeds? So what's the actual picture of accretion onto the planet?
I see. So yeah, the accreting gas is a bit hot, so the temperature can reach to a few thousands of Kelvin. But the accreting velocities, as I showed, the free fall velocity is a few tens of kilometers per sec. This is much higher than the sound speed in a few thousand Kelvin. So Mach number is larger than several and larger than 10 in some case. So strong shock, we assume strong shock here. So this temperature comes from the Rankine-Hugoniot's diabatic shock limit. So here, we assume the strong shock and calculate the temperature of the just after the shock, and calculate the numerically calculate the cooling after the shock. So is it answer to your question? So we assume the strong shock.
It does. Thank you.
Thank you for question. So this is the temperature profile. And this is abundance of the hydrogen-related chemical species. Here, okay, so yeah, here, this is a bit controversial to the temperature of 1000 Kelvin, but here we assume the H2, the hydrogen is in molecular form because, yeah, we calculate the radiating, roughly estimate the pre-shock temperature. And for this velocity and density, we assume, we get the gas temperature is around several hundreds Kelvin. So we use, so we assume the hydrogen is in the molecular form. So at first, molecular hydrogen dominated over the other hydrogen species. But due to the shock heated hot temperature, this molecule starts to dissociate quickly. And then after the dissociation, the ionization is also proceeding. So green is a free electron and orange is a hydrogen ion. And collision between the electron, free electron and the atomic hydrogen produce the excited hydrogen. The N equal 2 is red and N equal 3 is blue. And as I said, H alpha coming from the de-excitation from the N equal 3 to 2, so green, blue to red. So by using this distribution of the excited hydrogen, I calculated the radiated transfer of hydrogen line. So this light panel shows the result. So this black line is the Lyman alpha emission, and this red line is the H alpha emission, which is the observed one. So as you see, the Lyman alpha is very bright, and most energy incoming to the shock is converted to the Lyman alpha, but around 1% of energy, shock coming energy, is converted into the H alpha. And as I talked later, this 1% of energy is enough to be observed for hydrogen line H alpha. So this is one example of the numerical result. And yeah, I did a parameter study of the this kind of the numerical model. The vertical axis in this figure corresponds to the H alpha energy flux, and the horizontal axis corresponds to the B0 and N0. And the color represents to the initial parameter not in the horizontal axis. So here the gas density, and here is the gas velocity. So firstly, as you see, when the gas velocity is less than 25 km per sec, there is no significant emission of H alpha. Or this is an emission limit for the H alpha emission, the velocity limit. And larger than this velocity, you can see the power law in this log-log diagram. And actually, this is the power law index is 1 for number density and 3 for gas velocity. And as you see, this dimension is the same as the energy flux of the gas flow. So this means H alpha energy flux is proportional to the incoming gas energy, and the conversion fraction is, as I said, is around 1% or so. So 1% of the incoming energy to the shock is converted in H alpha, we found. Okay, so now we got the energy flux and the velocity. And yes, please.
Sorry, I apologize. One more question, if I may. So
yes,
I'm just still trying to understand the physical setup of the problem. So are you assuming that your planet and your disk are both just moving at a Keplerian velocity? So you know, locally, every particle in the disk is moving at a Keplerian velocity. Okay, other than the sound speed, of course, and the planet is also just in a circular Keplerian orbit.
Yes.
Okay.
But we assume actually this numerical model is in 1D. So the gas velocity the gas is moving in the perpendicular to our 1D model, but we don't care about the such direction. So we assume to get collide with the gas planet and the falling gas, but we assume the rotating velocity is mostly same between the incoming gas and the rotating planet. So yeah, I can say we are on the rotating frame in such a direction, and we only calculate the 1D perpendicular to the shock surface or planetary surface. So we don't care about
I was just wondering if the protoplanetary disks have sufficiently significant viscosity, for example, that they might not be locally moving at exactly the Keplerian velocity, right? Because as you say, you are operating under the assumption that the escape velocity at the surface of your planet is much larger than the let's say than the sound speed, and therefore by construction, and you're assuming it's much larger than the relative speed of the gas at infinity and the planet, right? But if the gas were somehow kept non-Keplerian because of some disk viscosity or something like that, then that could actually change the relative velocity at infinity and would change the setup of the problem.
I see.
So I guess my question is, and pardon my ignorance, but how well do we know that the gas in protoplanetary disks is really locally Keplerian?
Yeah, actually, when we assume the magnetic accretion, it's not so important because, here we assume there is a large gap, and the inner edge of the circumplanetary disk is 3 times, or around 3 times larger than the planetary radius. So the gas velocity, the gas rotating velocity here is not so important in this model. And in reality, not the free fall velocity, but 80% or around so of the free fall velocity. But for simplicity, we assume free fall velocity, and we can do some correction for such a non-infinity free fall velocity. How to say? But for now,
I think this is an interesting discussion, but let's try to keep the questions for the end of the talk, maybe. So let's just
I apologize.
Yuhiko finish his talk, and then
of course
we'll have time for questions. Thank you.
Thank you. Thank you for question. And actually, not only for the MHD, such a magnetic accretion, I have some accretion flow related to this shock in last of the talk. But I have time. I can talk about it, I think. And now we can get the relation between the energy flux of H alpha and the gas, the shock parameter, velocity and density. But what we want to know is not the shock itself, but the planetary accretion. So I convert this shock velocity and shock property into the planetary property. So here, as we discussed, we assume free fall velocity. This is assumption for simplicity, but it's not so bad assumption, I hope. And this is this equation comes from the free fall velocity equation, and we can get the planetary mass by using the shock velocity. And when we assume the shock surface area, we can get the mass accretion rate by using the shock velocity and density. And here, this F is a filling factor. This means shock surface fraction, shock area fraction to the planetary wall area, for surface area. And here we assume filling factor equal 1 because, as I showed, the energy flux of H alpha is proportional to M0, the gas density. So when we reduce the filling factor, then the emitting area is reduced. But due to the concentration, the gas density is getting higher. So these effects are canceled each other. So for the H alpha luminosity, the filling factor is not so important. So we assume filling factor equal 1 here. So this is a result of the such conversion. So also we assume we use the atmospheric model of accreting planet and get the relationship between the planetary radius and the mass accretion rate. So we can convert the B0 and N0 into the planetary mass and mass accretion rate, and get the H alpha luminosity as a function of these 2 parameters. So this is a result. The color shows the H alpha luminosity, and here the line contour corresponds to the observational result for PDSMT B and C. So yeah, for example, so we can get the relationship between the accretion rate and planetary mass for the observed planet. So for example, when we assume planetary mass is 10 Jupiter mass, then the PDSMT-B's mass accretion rate is 10 to minus 8 Jupiter mass per year or so. We can get such a constraint on the accreting planet. Yeah, also let me briefly talk about the L accretion and LH alpha relationship. So L accretion is accretion luminosity is the energy of the accreting gas per unit time. So the expression is this one. So this accretion luminosity to H alpha luminosity relationship means conversion efficiency of the accreting energy to the H alpha luminosity, H alpha emission. So these points correspond to our numerical result. And in this region around the H alpha luminosity expected for the planet, we can get a good fitting line to our numerical results. And as I said, this means, roughly speaking, the conversion efficiency is around 1%. And actually, for stellar case, this accretion luminosity and H alpha luminosity is given empirically. So in stellar case, we can observe the UV continuum and get the accretion luminosity directly. And by using the H alpha luminosity H alpha observation, we can get the H alpha luminosity. So we can get such a relationship empirically in stellar case. And before our numerical model, there is no theoretical model specified for the planetary accretion, planetary H alpha. So people try to use this empirical relationship to get the accretion luminosity or mass accretion rate of the planet. But as you see, for PDSMT-B, this is the luminosity of the PDSMT-B's H alpha. So our numerical our result and such stellar relationship differ larger than one order of magnitude or so. And in some cases, so actually this blue line mainly focus on the subsolar mass object, and this gray line focus on the low mass object, M dwarf or brown dwarf, and they have a bit different relationship. But yeah, for this blue one, yeah, actually some paper use this relationship for the PDSMT-B, but this relationship goes to this dotted region. So this dotted region represents the region the accretion H alpha luminosity is greater than accretion luminosity. This means the conversion efficiency is larger than 100%. So it seems unphysical. So at least for PDSMT-B, it's not valid. It's invalid to use this relationship to denote the H alpha to estimate the accretion luminosity. And also, as I said, the accretion conversion efficiency is roughly speaking 1% because most energy is emitted as Lyman alpha. So in the shock emission model, we cannot improve or increase the efficiency or conversion efficiency. So I think this stellar relationship is differ in planetary case and stellar case. Okay, so now we are talking about the H alpha luminosity, but actually we also have the spectral profile information of the planetary H alpha. So actually this is an observational result with MUSE BLT. MUSE is the name of the instrument and BLT is the name of the telescope, very large telescope. And this MUSE is not only for the photometry, but for the spectroscopy. So fortunately, we can also use the spectral profile of the H alpha to get some information about the accreting planet. This is a zoom up figure. This red line corresponds to the observational result, and this orange line corresponds to our numerical result. So our resolution, spectral resolution is a bit higher than the observational one. So by using smoothing with instrumental resolution, we can get these blue squares So as you see, when we choose a good shock parameter or planetary parameter, then we can reproduce the observational spectral profile. So now let's see how to choose a shock parameter or how to constrain the shock or planetary parameter by using this spectral profile. So this is the model result for the spectral width. This left panel shows the result for the H-alpha 10% width, and right panel shows the 50% width. This means the spectral full width at the energy flux is half of the maximum or 10% of the maximum. By using these two widths, I constrain the shock velocity and density. As you see, for example, for the PDS-MTP, black one, they have different tendency in the 50% and 10% width. Also, actually, this solid line is the mean of the observation, and this gray shadow region is uncertainty of the observation. And because of this different tendency, when we take this line into one figure, we can get the cross point of this mean solid line or a crossing region of this shadow. So this means by using the spectral profile, we can constrain the shock velocity and density. So for example, for PDS-MTP, the preferred gas velocity is 145 km/sec, and the density is 7 times 10 to the 13 per cubic centimeter. And also, as I told, we also have the flux or luminosity information. So by using using the luminosity information, we can get more good constraint on the planet. So in luminosity, filling factor is not so important, but in this profile, the gas density is really affects on the spectral profile. So we can get a constraint on the filling factor of 5 times 10 to the minus 4 for this planet. So this means the shock region is really concentrated in the small region of the shock planetary surface. And also by using this information, we can resolve in luminosity, we can get the relationship between the mass and mass accretion rate. But by using this spectral profile information, we can get individually we can get the mass and mass accretion rate of the planet. So from this spectral profile, the estimated planetary mass is 12 Jupiter mass, and mass accretion rate is 4 times 10 to the minus 8 Jupiter mass per year. So yeah, this is a better constraint on the PDS-MTP. And also, actually, we have other information for this planet. So this is a non-detection of H-beta. So actually, the MUSE instrument covers the H-beta's wavelengths. So if H-beta is bright enough to be detected, then the H-beta should be detected in the same observation. And this upper panel shows the H-alpha observation. The vertical is the signal-to-noise ratio. And in H-alpha, we can clearly see the H-alpha line. But in H-beta wavelengths, we cannot see anything because due to the photospheric noise. So yeah, unfortunately, H-beta was not detected, but the detection limit is given. So the upper limit of H-beta or the H-beta to H-alpha ratio upper limit is 0.28 for PDS-MTP, for example. So actually, this is very important, or this is good information for the PDS-MTP, because this left panel shows the H-beta over H-alpha ratio from our numerical model. So this blue line, bottom blue line, corresponds to the 0.28 of the H-beta over H-alpha ratio. This is the upper limit of the observation. So the H-beta is darker than this line. So this means the velocity and density of the shock should be lower than this line. But as you see, judging from the spectral profile, the predicted or preferred gas density is this one. and velocity is here. So around here. So in this figure, around here, the H beta over H alpha ratio should be unity 1. So H beta should be detected in the previous observation, judging from this theoretical model. So to explain this non-detection fact, we introduced the extinction of the hydrogen line. So we assume the power law of extinction coefficient of minus 1.75. This is a power law for the interstellar medium. And in this case, in this assumption, the shorter wavelengths have stronger extinction. And H beta is shorter than the H alpha in wavelengths. So the H beta should get a higher or stronger extinction than H alpha. So strong extinction can reduce the H beta over H alpha ratio in observational point. So this each line corresponds to each extinction coefficient. So A is the magnitude of the extinction. So when we assume 0, then the ratio should be here. But when we assume extinction coefficient equal 1 magnitude, then here. And when we assume 2, then here. So if we assume the extinction coefficient at H alpha is around 2.2 magnitude or so, then the non-detection of H beta can be explained. So this fact of H beta non-detection infer the hydrogen line from PDS-70b should have strong strong extinction. Okay, so this is a constraint on the PDS-70b by using the line information, observation of line and theoretical model. So for last, I will talk about how to generate such a strong shock on the planetary surface. So in the first of the talk, I told about the magnetic-spheric accretion. So the planet, the circumplanetary disk have large cavity between the planet and CPD, and gas falls from the CPD to planetary surface directly. But this requires strong magnetic field of the planet. Then without magnetic field, is there no strong shock and no emission? And my answer is no. So magnetic field is not required. So this is a schematic figure of the gas accretion to the planet. So this gray region is a heliosphere. In this region, the planetary gravity dominates over the stellar gravity, and the outer region is a protoplanetary disk. So when the gas try to enter to the heliosphere, in mid-plane, the gas cannot enter to heliosphere due to the potential barrier. So instead, the gas enter to the heliosphere in high altitudes. So gas enter to the heliosphere, fall from the high altitudes to the CPD surface vertically. So this flow is really important, and this is not occur on the stellar case. This is specific for the planet. So this is important for the strong shock we consider. So this is a numerical result of the 2D simulation. So this is a vertical, so this is a mid-plane of the disk, and this is vertical direction. The gas falls from the high altitude to CPD surface, and after hit to the CPD surface, actually the gas start to move to the planetary surface or planetary direction along with the CPD surface. So this clamp-like high density feature goes to the planet, fall to planet. So actually, yeah, this flow can generate strong shock on the planetary surface without the magnetic field. So let's see this overview of this flow. So this is a schematic image of this flow. So this is the circumplanetary disk, and this is the shock surface or the disk surface at the point. And this is the gas flow direction. As this is the falling gas direction is not perpendicular to the shock surface. So after the shock, only the component of the gas velocity perpendicular to the shock surface is reduced by the shock. So after the shock, the gas direction changes to the direction to parallel to the shock surface or disk surface. So this shock changes gas direction and gas slip or slide on the planetary the disk surface and hit to the planetary surface and generates strong shock on the planetary surface. So this gas flow can generate strong shock on the planetary surface and strong emission of H-alpha. So this is the density and velocity of such flow. The horizontal axis corresponds to the latitudinal angle. So 90 degrees is the mid-plane of the disk, and 0 is the pole of the planet. So in mid-plane, the gas density is really high, but as you see, the radial gas velocity is low. So as I told, if the gas velocity is less than 25 km per sec, there is no strong H-alpha emission. So mid-plane cannot contribute to H-alpha emission. In polar region, the gas velocity is really high because some gas can freely fall from the PPD to planetary surface directly. So gas velocity is high, but the density is low. So this region is also have low contribution to H-alpha emission. So finally, in this intermediate region around the CPD surface, the gas velocity is high enough to emit H-alpha, and gas density is high due to the flow I told in the previous slide. So without magnetic field, this region is the main source of H-alpha we consider. So this is the H-alpha luminosity with time variation. So as I show in the numerical result animation, the gas creates some clamp-like feature, and the gas density have time variation. So H-alpha emission also have time variation in this case. So actually in the Hubble telescope time series observation of H-alpha, people know the H-alpha emission have time variability of the 1 order of magnitude at most. So yeah, this model maybe can explain such a time variation. But of course, also in the magnetic spherical accretion model, there is time variation. But in such case, the time variation should be related to the magnetic field structure. So it should be related to the spin rate of the planet. So spin timescale should be related to the time variation. But in this case, the perturbation, time variability comes from the perturbation on the CPD surface. So the time scale is longer than such spin time scale of the planet. So maybe by using such the time variability time scale, we can get some constraint on the gas flow, we hope. So that's all. So this is my summary. So in these days, direct imaging observation detected H-alpha from accreting protoplanets. So we made some numerical model, and we found that H-alpha spectral profile and luminosity enable us to determine planetary mass and mass accretion rate. And the planetary error accretion luminosity to H-alpha luminosity relationship is different from the stellar one. So we have to make or construct a specific model for planet. Also, multiplying observation enable us to get more information, particularly on the extinction. Also, gas flow along with CPD surface leads to strong shock and strong H-alpha emission without magnetic field. So this is all. Thank you for listening.
Thanks a lot, Yuhiko, for this very interesting talk. Please join me in an unmuted clap for Yuhiko.
Thank you.
We have plenty of time for questions. Feel free to either raise your hand or type them in the chat. In the meantime, I have a few questions if there's none.
I've got a question.
Please go ahead,
remember
Rosemary.
how to raise my hand. No, I missed, first of all, I thought that was a fabulous talk. Really, really enjoyed it. I missed how far these particular planets are from the star, but I wondered about the role of the magnetic field of the star itself, and for shorter period planets, which I guess are harder to observe this way, how that might affect the results.
So the magnetic field. So
you might have said it and I missed it.
this one. So magnetic field. So this figure, right?
Yep.
So yeah, in this case, in stellar case, the magnetic field is very strong, and the ionization fraction in the inner disk is high. So the gas can couple with the magnetic field, and when the inner disk gas rotates faster, or Kepler velocity of the disk gas is faster than the planetary spin, the stellar spin rate, then the magnetic field is spin with the same speed of the central star spin. So yes?
Can I just jump in there? And what I meant was how the magnetic field of the star affects the situation at or affects the magnetic field of the planet. Basically, modifies the process. So I wasn't talking about accretion onto a star.
Mm-hmm.
Talking about the magnetic field of the star.
Mm-hmm.
Influencing what happens at the planet.
I'm sorry. So what's your question? So sorry, I can catch it.
Well, I'm thinking of the sun and its magnetic field and its interaction, and with the Earth's magnetic field, for example. So presumably, at least for shorter period planets. The magnetic
short period of planet. Okay.
No, well, not necessarily, but I mean, there's some distance from the star where the magnetic field of the star itself interacts with the magnetic field of the planet, and that ought to influence this, magnetohydrodynamical process.
I see. But in most cases, so there is some theory to create a short period planet. But when we consider about the migration from outer to inner, then the planet should stop at this point, the inner edge of the protoplanetary disk. So, but in some case, maybe the stellar magnetic field can affect the gas flow. I'm not sure about the emitting in such close short period planet.
Yeah. Well, anyway, it's just an added complication, and possibly for these longer period systems.
In long period systems, then the stellar magnetic field is negligible probably, but in such short period planet, maybe this prevent to the magnetic spherical accretion model for planet. Maybe the stellar magnetic field interact with the planet magnetic field and make some process. So, it's interesting, but sorry, I have no comment on this.
No, that's okay.
I actually have a related question to Rosemary's, if I may jump in. So I was wondering whether we would expect the magnetic field of the planet to be strong enough to trigger magnetospheric accretion. Isn't there a minimum magnetic field strength required for that kind of accretion to have magnetic accretion flows dominate instead of boundary layer accretion? And what would be the requirement, say, compared to today's Jupiter's magnetic fields strength? Would it be much larger than that to have magnetospheric accretion?
So actually Jupiter magnetic field strength is people consider that it's not enough to make such a accretion flow. But in the actually this is a simple scaling law, but in some people consider that a young gas giant have a much stronger magnetic field than the current Jupiter. So it can be a few gauss or a few sub-gauss of magnetic field, then people consider that magnetic field is strong enough to couple with gas flow, and magnetic accretion can be occurred. But there's no solid evidence for such a accretion flow for now. So maybe time variability observation can say something about such a accretion flow.
Yes, that was my follow-up question. Actually, if with your model you could disentangle between those two types of accretion based on the H-alpha luminosity or the luminosity of different hydrogen recombination lines, or the ratio, like you also presented H-beta expected luminosity, would that be able to constrain the type of accretion, maybe based on the velocity that would be involved to create those luminosities, the observed luminosities of different hydrogen recombination lines?
So for example, when we get some other line, except other than the H-alpha, H-beta also, then for now, so we have only detection limit of H-beta and only one line, or including H-alpha, only we have 2 lines. So by using these 2 lines, if we get the H-beta luminosity, then we can say anything with only 2 lines. But if we get another 1 line, for example, Paschen beta or bracket gamma or something like that, then we can check the validity of our numerical model by using such a 3 or more hydrogen line emission. So for 2 lines, we can say anything if we say the extinction, if we change the extinction coefficient. But if we can get more lines, then I hope we can constrain, or we can check the validity of the model, or confirm the extinction or velocity or the density of the gas.
Right, thanks. Is there any other question for Yuhiko? Otherwise, I do have another one. Actually, I have plenty of questions. And the question related to the filling factor. I think in one of your plots, your first result, I think you mentioned, you assume the filling factor of 1.
Yes.
So I was a bit confused about that. Would a filling factor of 1 be more representative of boundary layer accretion?
I see.
You do assume it covers the whole planetary surface. Than a very small filling factor, since you said, I think you could put some constraint on the filling factor. So would that suggest the accretion is rather following magnetic streams? So
I
is that
see.
correct?
Yes, true. It's true. It's correct. Here for simplicity, I assume the filling factor equal 1 because as I said, the filling factor is not so important for this this diagram. So we can assume any filling factor. So for example, 1% or 0.1% is okay. But for simplicity, I assume this one. Sorry, so for confusion. So by using the spectral profile, as I briefly said, the small filling factor is preferred by this spectral profile. So for this case, 5 times 10 to the -4. And this is consistent with the magnetospheric accretion. In such case, the accreting gas should concentrate in the small region of the magnetic field is concentrated. So this small value is consistent with such a concentrated gas flow. But actually, as you may know, the spectral profile of the P70B is people says this is not well resolved. So this broadening width is close to the instrumental resolution or instrumental broadening width. So some people says this profile is not well resolved and the gas width is overestimated. So maybe this is not the solid solid answer or solid fact. But at least by using this constraint, the small fraction is preferred. Yeah, as one of the fitting factor is not reasonable. True.
Oh, thank you. I was muted. Sorry. Actually, related to that, I was wondering in your plot where you showed the total accretion luminosity versus H-alpha luminosity. I noticed that for small accretion rates, there was no dependency on the filling factor, while for high accretion rates, you'd expect, yes, on your slide 17.
I see.
Yes. So for low values of H-alpha luminosity, I see that all your predictions converge to the same total accretion luminosity, while for larger H-alpha luminosity, you start to see different behaviors for different filling factors. Could you explain why?
Okay, yeah, thank you for the question. So actually, this is related to the absorption of the H-alpha. So yeah, here we don't care about the extinction or absorption, between the shock surface and us. But here, the absorption in the shock heat layer is important. So, okay, yeah, this is the case for the high density, and this is a radiative transfer of H-alpha. So H-alpha is emitted in deeper region and radiatively transferred to the upper region. But here, as you see, there is a decrease of H-alpha luminosity. So because this is in the log scale, this seems very small. But yeah, in the linear scale, this is not factor 2, but yeah, a few or several tens of percent. No, a few tens of percent decrease. So this absorption effect is visible in this case. So this case, the H-alpha or accretion luminosity is high, and this means gas density is high. And filling factor, small filling factor means high density because the gas is concentrated in the small region. So in such dense case, the gas absorption of H-alpha is visible, and the H-alpha conversion fraction gets lower. So yeah, in such case, for high dense case, the filling factor is not negligible for accretion luminosity, for H-alpha luminosity.
I see.
But in most case, for reasonable parameter, we consider it's negligible. But in some case, it's not the case.
All right, thank you. So we have time for one last question. Someone wants to jump in? If not, I'll just go with a last question. Could you comment on your assumption regarding free fall velocity?
I see.
So in case of magnetic flows, would that be close to the velocity you'd expect?
I see. So, okay, so for example, in this case, so in most cases, so for especially particularly for the higher mass planet, the planetary mass is not important for the H-alpha luminosity. This means the planetary mass is highly related to the gas velocity. So this means the gas velocity is of course important, but not the main, or how to say, the gas number density or accretion rate is more important for the H-alpha luminosity. So yeah, the free fall velocity is maybe not valid for some case, but yeah, for example, 10 or 20% reduced of the gas free fall velocity or gas velocity is not so fatal to the estimate of H-alpha luminosity we consider. Also, yeah, in this case, so for the case of the the CPT surface accretion, we consider about we didn't assume the free fall velocity, but use the numerical result velocity. But the estimate is not so different from the assumption of free fall velocity. the point is, the most important point is gas accretion rate or density.
Okay, thank you. Thanks a lot. Let us all thank again Yuhiko for this very interesting talk, for answering our questions.
Thank you for listening.